My name is Matti Järvisalo, and this is joint work with Järvisalo and Brandon Malone in the corner over there. Yeah, so as the title says, I'm going to talk about learning optimal bounded-Treewidth Bayesian networks using a specific constraint optimization paradigm called maximum satisfiability. So the underlying motivation here is that while exact probabilistic inference in general over Bayesian networks is NP hard, it's actually tractable over networks that have low tree width. So here our challenge is to develop algorithms for learning optimal bounded tree width Bayesian network structures. So optimum is with respect to a scoring function. And bounded tree width means here really low tree width, so some sort of a non-trivial bound on the tree width of the networks, not say the number of nodes. A constant bound on the tree width. So our contributions are basically an approach for learning these structures. So learning provably optimal and provably bounded Treewidth Bayesian network structures, and we're using constraint optimization tools for this. Well, I'll show you some results that basically show you that we're significantly outperforming the state of the art from actually last year's AI Stats conference. Well, I'll go quickly through what are Bayesian networks and structure learning problem, which you all likely know, and then try to give an intuition of what I mean by tree width, and try to get into this idea of how we actually use constraint optimization solvers to solve these optimal bounded tree width structure learning problem and show you some of the results. So, okay, as you all know, a Bayesian network structure is just a directly acyclic graph, a DAG, where the nodes represent some random variables, x1 through xn. And then we're basically given a scoring function that tells, is a measure of how well a specific DAG fits some observed data over the random values. And as typical, we're going to assume that the scoring function that we're given decomposes into so-called local scores over the variables. So basically, a DAG is represented by a set of, by choosing a parent set, the parents for each node in the DAG. So this set for each node I is called the parent set of the node xi, and then we can just sum up the scores for the parent sets, and that gives you a score for the DAG. And in our exact sense, we're looking at the structure learning problem as the following problem. So we're just giving a set of local scores, SCPI, so SI, for possible candidate parent sets for each of the nodes I. And our task is to find a DAG that minimizes the sum of the local scores. So find a G star, which is a DAG, and minimizes this sum. So of course, this is a central problem, and there's been a lot of algorithmic work on it. So the earlier algorithms are typically based on our so-called inexact algorithms, by which I mean that they do provide some solutions, but they are not guaranteed to be optimal. And there's been more recently quite a lot of work on actual algorithms that do give these optimality guarantees, based on, say, dynamic programming, and then later on using heuristic search algorithms and integer linear programming. Okay, so after learning a Bayesian network from data, one would want to do probabilistic inference, and as I mentioned, there are computational challenges actually in both of these steps. So first of all, finding an optimal Bayesian network structure is an NP-hard problem, and so is exact probabilistic inference over Bayesian networks. So we're sort of dealing with too hard for our problems. One notion that alleviates one of these hardness factors is Treewidth, which is just intuitively a measure of how close a given undirected graph is from being a tree. So intuitively, trees basically have Treewidth 1, and complete graphs over n nodes have Treewidth n-1. So whereas learning optimal bounded tree with Bayesian network structures is still NP hard, if you can do this fairly fast, then you're bound to actually be able to perform polytime exact inference over these structures that you learn. And while there's been quite a lot of algorithmic work for the original problem without the Treewidth bound, the Treewidth constraint, there's been fairly few algorithms proposed for this under this Treewidth constraint. What I know of is the sort of a hill climbing based local search algorithm from 2008, and then the first exact, so guaranteed optimal solutions providing algorithm was presented at AI Stats last year. I should mention that there is parallel work to our paper actually published also here in this conference where an alternative constraint optimization approach is presented using integer linear programming. I won't have time to get into the similarities and differences, but I'll be happy to mention some if you want to learn after the talk. Learn more about it after the talk. Okay, so what's Treewidth? Well, first of all, for undirected graphs, it's defined for undirected graphs, and here's a nasty way of saying what it is. It's the minimum, the maximum out degree over the possible so-called ordered graphs of a given graph G. Well, what does that mean? Well, here's an undirected graph for you. So if we fix a total ordering over the nodes of this graph, we can do a so-called triangulation step using that ordering, which means that we basically look at pairs of nodes, and if there is a node that's connected to both of these nodes, let's say x1 and x4, and look at x2 here, and x2 is actually a predecessor in the ordering of both x1 and x4, and in this case we will introduce an additional edge between x1 and x4, and you repeat this until you reach a fixed point, and that gives you the triangulation of this graph under this specific ordering. And you basically simply get the so-called ordered graph under the ordering from the triangulation by ordering these undirected edges according to the order. Okay? So how do you define the Treewidth of a Bayesian network structure? Well, you basically just do an extra first step or zero step where you so-called moralize the network structure, which is just a DAG here. And, well, by magic, it happens that the moralization of this DAG is that guy. How do you get it? Well, you get it simply by including an undirected edge here for each directed edge here, and including an undirected edge here if the corresponding nodes have a common successor, common child. So actually, the moralization of this DAG is that guy, where we added this edge because x6 is the child of x4 and x5. And now I said under a fixed or total order, and so that basically gives you, then you can, for that order, you can just look at the graph and figure out the maximum out degree of the nodes. But now, to find the minimum over all possible ordered graphs, you have to go through all orderings of the nodes in some manner to find a so-called optimal order that will give you the minimum of the max out degree. And that is the tree width of the Bayesian network structure. Okay? So we want to learn these bounded tree width Bayesian network structures. So here's the problem. The red stuff is the new added things compared to the original problem without the tree width constraint. So we're basically given the local scores for each xi for the candidate parent sets and the tree width bound W. And now, again, we are to find a DAG that minimizes the decomposable scoring function, but we're restricting to DAGs that have tree width at most W. Okay? So it's a constant tree width bound. And this remains an NP-complete combinatorial optimization problem. So actually, the tree width bound is really a non-trivial additional constraint to the structural learning problem. And in fact, determining tree width of the tree width of a graph, of a given graph, is in itself an NP-hard problem. Basically, it's about learning the optimal, finding the optimal node ordering. Optimal node ordering. Okay, so getting to how we solve this problem optimally is by using constraint optimization tools. So again, we're assuming as input these local scores, SIs, and the tree width bound. And we do a declarative constraint, we do a constraint declaration of the problem, which actually consists of the following 4 constraints. So for each node, we are to choose exactly one of the candidate parent sets, so as we'll have a graph that's well defined. Then, because Bayesian network structures are acyclic graphs, we are to guarantee that we should only allow such choices of parent sets such that we'll get an acyclic graph. And now, getting to the tree width constraint, we declare basically what's the moralized graph of a graph that we look at, and have to state declaratively that that guy's tree width should not succeed the tree width bound W. And of course, as I said, we want to learn optimal solutions. So the G star that we're looking at should minimize the decomposable sum, the objective function of the problem. So this is in an abstract setting. So there are a lot of constraint optimization tools, a lot of constraint optimization languages. So now, if you want to go this route, you have to actually figure out what constraint modeling language should you choose. It should be somehow appropriate. One is that it should actually capture the class NP, because we want to solve an NP-hard problem. And then we have to figure out a way to use that specific language to, in a suitable way, declare these constraints, these abstract constraints. And once we have that, hopefully we chose a language that actually has an efficient constraint solver that can actually provide these optimal solutions for the constraint declaration. So we just feed them the constraints to the solver and wait for a solution. And if we did all of these steps using some intelligence, we might actually get something that gives us actually a state-of-the-art approach to solving the problem. What we did here is use a very low-level constraint optimization, modeling language called maximum satisfiability. So really shortly, this is what I know most about. Actually, but I assume that you don't. So in MaxSAT, we're dealing with really low-level constraints called clauses that are basically logical ORs of Boolean variables. So we're allowed to use only Boolean variables and declare logical disjunctions over the variables and their negations. So here's one clause. So it says x1 should be true, or y should be false, or z should be true. And these are the only types of constraints. The arity of the constraints can be whatever, but these are the only types of constraints. So the MaxSAT problem is we're given a set of clauses and actually weights for these clauses that allow us to encode objective functions, basically. So here's W is a weight for the clause. It can be infinite, which means that we're dealing with a hard clause that any solution has to satisfy, which means that any solution has to satisfy the clause. And if we declare a finite weight for the clause, we basically have a soft constraint that says that either you satisfy the clause or you get a penalty according to the weight. So you incur a cost of W. And the task then is to find a solution, an optimal solution to this set of clauses, which means that we minimize the cost incurred by those clauses that we do not satisfy. So this looks really low level and really weak, but it captures NP-hard optimization problems, and it actually gives a viable way today to solving real-world NP-hard problems. And it actually builds on the success of so-called Boolean satisfiability solvers. If you want to know more, come and talk to me. I'll tell you as much as you want to hear about them. OK, so how do we then, just to give you some sort of an idea, how do we do these constraint declarations? So here are some key points. So we have to use Boolean variables. So we're going to use so-called parented variables, PIS, which means that node I gets as its parent set S, if this guy is true. Then we use Boolean variables to represent the edges in the moralization of a DAG, Mij. And then we use, similarly, OIJ variables to represent the ordered edges, and Boolean variables for representing the ordering, which means that ordered IJ means that I comes before J in the ordering. And now the point is that we basically have to implicitly go through all the possible combination, the value combinations over these variables under some constraints that specify the abstract constraints 1 through 4 that I was talking about. How am I doing on time? Sorry? How am I doing on time?
You're fine, 5 minutes.
OK, good. So for some intuition about how the constraint declaration actually works is that we're basically starting non-deterministically from the choice of which of the PIS, the parented variables, are true. These guys induce the moralized graph, Mij variables, the assignments to the moralized graph variables. Pretty much according to what the moralization process means, the definition of a moralized graph is. And then once we have these Mijs and a choice of an ordering over the nodes, these guys will induce us the ordered graph. And then we enforce the Treewidth bound W over using these OIJs. I won't go through many more details, but here's just so that you get some flavor of how the MaxSAT declaration looks. Let's look at how we actually encode the objective function. So the objective function says that if we choose a specific parent set S for a node as xi, we should get a penalty according to the score of the parent set S, right? So how do we actually declare this as a clause? Well, for each choice of xi and s, we simply introduce the clause not PIS, which means that we do not choose S for PI, for the node I. And we set the weight of the clause as according to the score of S for the node I. So this means that, simply means that either we don't choose S for xi, or we get a penalty according to the cost, the score of S, right? So the other parts of the encoding are more intricate. So, for example, we have to enforce this exactly one parent set choice for each node, and which means that we have to somehow encode with clauses this sort of a linear equality. Well, for this, there are a lot of work. There's actually a lot of work how you can encode these sorts of inequalities in a MaxSAT. I won't get into that. Similarly, you have to be fairly clever in how you enforce acyclicity, because you can't do a cubic encoding, a transitivity thing that would say like, if x is before y and y is before z, then x is before z. That's too costly. So we do some sort of use bit representations to shorten the encoding, and so forth. So finally, some results. So we used some standard UCI data sets going up to some 30 nodes. As a scoring function, we used MDL. Any scores would do. I don't care. Give me scores. Let's solve it. And we did some typical pruning of the data sets and used Treewidth bounds 2 through 4. We choose as the MaxSAT solver, a recent solver that actually can handle these sorts of scores that we have to deal with very well, called MaxHS, and compare it to the dynamic programming algorithm from last year's AI stats. And here are some of the results. So our approach is here titled MS, and the last year's approach is DP. So what you basically see is that DP does somewhat well on the small instances, well, especially here. But actually, the problem with DP is it's using a lot of memory. So first it starts to time out, but then it runs out of memory. And as you increase the Treewidth bound, it just runs out of memory. Whereas basically, our approach, even if it actually does provide provably optimal solution, it really, the running times are not sort of, don't scale according to the number of nodes. They somehow implicitly tend to scale in terms of the structure of the data on which the instances are based on. But this is just some hypothetical intuition. Okay, so that's what I had to say. So this is a novel approach to learning optimal Bayesian network structures under Treewidth constraints. There hasn't been much work until now on this problem. I tried to give you some idea of what's MaxSAT and how you can actually use a MaxSAT solver to solve this problem. Come and talk to us for learning more and check out the paper. That's basically what I had to say. Thanks very much.
Questions?
Thank you. Very interesting talk. In many applications, you might not be interested only in the best network structure, but in a distribution. So if you have some limited data, you might want to capture uncertainty as well. So how involved would it be to actually go from the optimal structure, conditional on a Treewidth constraint, to some estimation of the whole distribution? So I'm wondering, so along the lines of the algorithm on your slide 13, so you sort of relax the third constraint, considering different alternative parent configurations which might have similar scores. So basically, in some ways, the Friedman-Koller paper 2003 on looking at getting whole distributions of DAGs, how involved would that be to get a distribution of DAGs conditional on a tree-width constraint?
Well, basically, how you would go in a naive way, you can basically iterate, solve again and again, and we can just state constraints saying we don't want to see these solutions that we've seen so far. And you can actually sort of learn the best, however many networks you want. Not maybe an exponential number of them, but some number of them before we actually get into problems. We haven't tried this, but this is what you can do. So let's say you could, I think, easily learn the 1,000 first networks. But to learn them all somehow, estimate the whole distribution, I can't give a good answer to that right now.
Other questions?
So thanks for the nice talk. And so when you go to the experimental section, I found out the number of variables are still, is still very small. And did you, try to use some kind of like a test data and also some kind of approximate algorithm to, test the log likelihood of the test data, based on different your algorithm, the dynamic programming, and the approximate algorithm to see, which one works best and how, well your algorithm. So based on this kind of MaxSAT can, can beat the baseline.
Beat in terms of
just for example, just some heuristics for learning the bounded tree width. I think there are lots of such kind of variants.
We haven't tried these non-optimal, let's say, these inexact algorithms that don't give you the optimality guarantees. No, but I'm quite sure that even for these node numbers, you won't be able to, even if they couldn't. It's not that they can't prove optimality, but I'm quite certain that they can't even find an optimal solution.
Still, based on the this kind of constraint satisfaction, I don't know. You can find the optimal, the structure with the bounded tree width. Where's the proof? Did you have any kind of proof that, this kind of MaxSAT?
Oh, this is guaranteed. Yeah, I mean yes. I mean it's just that yes. So there's no. It's guaranteed that this will provide optimal solutions. There's nothing fuzzy about that. So the constraint declaration is entirely faithful to the objective function, and it really in parts encodes the problem exactly. So it does find optimal solutions. That's a key point. Yeah.
Thank you for talk. Can I ask a question about the Treewidth tree about horse?
Mm-hmm. Oh, yeah. Okay. Yeah. So the MaxSAT solver is based on some heuristics. So it's guaranteed to find optimal solutions for any MaxSAT instance. But it just happens that, for example, I don't have a good explanation other than that it just happens that in this particular case, the instance happens to be unsuitable for the specific solver. So it's just goes into the wrong direction first and spends a lot of time.
So you have tried different runs. It shows the same result. All of them goes to the larger than 8 hours.
Sorry.
I mean,
try different what?
Try different experiments
different solvers, you mean?
No,
or?
I mean, is it just you do it once, or you do have to several times?
No, okay. So the solver is actually deterministic. So there's nothing random. It's not randomized at all.
Okay.
It's not randomized at all.
More questions? No? Well, thank you.
Thank you.
And thank you.